Good evening, everyone. We are in the week 5 problem solving session of the NPTEL course, Network Analysis. And week 5 has two parts. The first part being solution to linear differential equations with the forcing function as x of t is equal to delta of t, which is impulse function. And the second part being self and mutual inductance of a coil. Let me share my screen. So here we have the week 5. So first I'll be talking about an impulse function. So the session will be going on in this way. For the first 1 hour or 45 minutes, we'll be discussing about the impulse function and how to get the solution to a linear differential equation if the forcing function is impulse function. And in the second part, second 1 hour, we'll be discussing about the self and mutual inductance and how to solve a given circuit if it has self inductances as well as mutual inductances. So first part is solution to linear differential equation with the forcing function as impulse function. So the first part is solution to LD means linear differential equation. Linear differential equation with the forcing function x of t is equals to delta of t. Okay. But before we go into the solution of or solution to linear differential equation with this forcing function, I want to explain or discuss about what is an impulse function. So first we'll discuss about impulse function. Okay. What is an impulse function? Say I have considered a function. Say this is the time period t, and hello, Maunika, am I audible? So this is my delta of t, and say I have considered. Hello, Maunika, can you hear me? Hello. Hello, Maunika, can you hear me? If you can hear me, just mention in the chat box or just let me know. Hello. Hello, Monica, can you hear me?
Yes, sir.
Okay, okay. And can you see my screen?
Yes, sir.
Okay, thank you. Thanks for confirming. So delta of t, say we have a rectangular waveform with this width being h and the height being 1 by h. So h is the width, so it is on the either side of t equals to 0. So this point, this center point is t equals to 0. So now what is the area of this impulse function? So delta of t has area is equal to h into 1 by h is equals to 1. Okay, but impulse function has a limiting condition, that is this function is impulse function when h tends to 0. So as h starts tending to 0, the width of this function will be tending to 0 and the height will be tending to infinite. So 1 by h is tending to infinite, but the area is still 1. It's a hypothetical function, but it is the scenario, but area is equals to 1. So as the width gets smaller and smaller, the height becomes larger and larger, but the area is 1. So now if I use the formula, area is nothing but area under the curve is nothing but the integration, right? So I will be integrating from minus infinity to infinite delta of t dt, which is equals to 1. So this is one condition of delta of t. So the area of delta of t is 1. But the value of delta of t at t equals to 0 is infinite or undefined. So if we are asked what is the value of delta t at t equals to 0, it is infinite. And for the other values of t, it is 0. Okay, so we can say in a way that delta of t, this value is infinite when t equals to 0, and it is 0 when t is not equals to 0 during the entire time period from minus infinity to infinite. But from this, I can write, so delta of t is a function, if you see, from this region to this region. So if I consider this 0 plus and this 0 minus, so it starts from 0 minus to 0 plus, and within that region, the tiny region, its value is infinite, such that the area is equals to 1. So now I can also reframe this expression as area is equals to integral 0 minus to 0 plus delta of t, because the width is very small. It is just greater than 0 and just less than 0. It is symmetric. So 0 minus to 0 plus delta of t d of t is equals to 1. So it can also be written like this. Now, this is just some basic information about the impulse function. Now, the question is, so, okay, we have the impulse response, and we have a linear differential equation with impulse response, because in the previous weeks or earlier weeks, we have discussed the function x of t to be some polynomial, to be some constant, to be some sine or cosine or exponential, and we know the value at t equals to 0, boundary condition, but for delta of t, we do not know the value because it is indefinite. We cannot say it is some 10,000 because it is infinite. So we cannot uh, get the value of delta of t at t equals to 0. Now, then how to proceed? Okay, we'll come to one example that Sir has mentioned in his notebook. So, yes, this is the example just to understand how to solve linear differential equation, sorry, linear differential equation having a delta of t as input. So I have considered one problem from SAR's lecture material. So this is problem 1. One thing is we only have this condition, one condition, which we can use to solve any equation. So the integral from 0 minus to 0 plus is delta of t. Okay. So can anyone tell me how to proceed with this type of linear differential equations? Okay. As we know this condition, I do not know the value of delta of t at t equals to 0, but I know that the integral from 0 minus to 0 plus of delta of t dt is 1. So what I'll do is, I'll consider this given equation dy by dt plus 3y is equals to delta of t. Then I'll apply integration from 0 minus to 0 plus, 0 minus to 0 plus, and 0 minus to 0 plus. And accordingly, I will multiply by dt, of course, on LHS as well as RHS. So if we write the simplified or the modified expression, we will get 0 minus 2 0 plus dy plus integral 0 minus 2 0 plus 3y dt is equal to integral 0 minus 2 0 plus delta of t dt. Now one thing I know is I know this value is equal to 1. So my RHS is equals to 1. And this term integration of dy is y. So I can write this as y0 plus, or maybe I'll use a different color. So this term can be written as y of 0 plus minus y of 0 minus. Right. And what about this term? Anyone? Hello.
3y of 0 plus minus 3y of 0 minus.
Okay, but actually here we are integrating with dy. Here we are integrating with dt. So it will be integral of y from 0 minus to 0 plus. And okay, before we get into this thing, let me consider, say, one thing. If we have this type of equation, so you know about step function, right? Maybe I should cover that step function, which is u of t. U of t is like from t equal to minus infinity to 0, it will be 0, and then it will have a step function 1. Now, what will happen if we differentiate u of t with respect to t? So, my question is, what is du by dt? Okay. What will be du by dt? Du by dt will be, say, if I draw, first I'll consider t less than 0, then I'll consider t greater than 0, and then I'll consider t equals to 0. See, t less than 0, it is 0. T greater than 0, it is 0. At this instant, it is infinite. So it will be something like this, right? Which is also our delta of t. So differentiation of u of t is delta of t. So or integration of delta of t, we will be getting what? U of t. Okay. So yeah, if we go back here, as if y is having u of t characteristics and dy by dt is having delta of t characteristics. Understood what I'm trying to say over here? Hello. Hello. Okay, so what I'm trying to say is if we consider u of t, which is a step function, and if we differentiate it, we'll get delta of t. Okay, and how delta of t, u of t are related? Integration of delta of t will give us u of t, because I'm going in the other way. Similarly, what happens if I integrate u of t? What happens if I integrate u of t? So it will be something called ramp function. And I hope Sir has taught this in the class. So ramp function is denoted by r of t, and it will be something like this. Okay, r of t is a ramp function having unit slope. It will increase like this. So I can say dr by dt is equal to, or dr of t by, I should write dr of t by dt is equals to u of t, and d u of t by dt is equals to delta of t. So why I'm saying this? Because here y of t is having, say, we have delta of t. So delta of t is coming from this term dy by dt. So dy by dt is having delta characteristics. So if we integrate that, or if we integrate dy by dt, we will get y. So y is having u of t characteristics, which means it is discontinuous at t equals to 0. So y of 0 plus and y of 0 minus are not equal. Now, if we integrate y, then we are integrating u of t. Then we'll get a ramp, and ramp is a continuous function. So r of t at t equals to 0 plus and r of t at t equals to 0 minus are close because it's a continuous function. The value is same. So if we integrate this from 0 minus to 0 plus, it will become 0. So this term value is 0. Okay. Why? Because again, there is this function called r of t, which is ramp function, and it is having a slope. Slope is equals to 1. If we differentiate that, then we'll get something called unit function, and it has a discontinuity at t equals to 0. And if we differentiate that, then we'll get this impulse function delta of t. So likewise, if I integrate delta of t, I'll be getting u of t step function. If I integrate u of t, then I'll be getting r of t. So the r of t integration from this region to this region, so it is around the origin point. The area is 0 because it is very finite value, 0 plus and 0 minus, and at that value r of t is same because it's a continuous function, and because of that reason this will be equals to 0. I hope you have understood this point. If you have any further query, you may ask. I see very less number of participants today. Okay, anyway, this video will be uploaded, so you can watch it later also. But those who are attending, if you have any queries, you may stop and ask. Sir, integration cannot be 0. Why? Hello, Naveen. I don't differentiation can be 0. I don't know. Okay, what I'm trying to say is, see, we are integrating in a very finite value tending to 0. So we are not integrating over a large time. We are integrating from 0 minus to 0 plus. It is actually 0, but these values, if you see delta of t, u of t, they are changing at t equals to 0. So at t equals to 0, you cannot define the value of that function because t greater than 0, it has a different value. T less than 0, it has a different value. So I consider, say, 0 plus to be 10 to the power minus 10. So 0 plus 10 to the power minus 10, u of t value is 1. And 10 to the power minus 10 to the power minus 10. So I am considering just a finite increment here. So this value and this value, if I consider the values of u of t, they are two different values. Whereas r of t, if I consider two values, so it is like this. So I will consider this value and this value. So they are very near to each other. So the value is very close to each other. So now if I integrate y of t, I'll get this r of t. So now I have to apply the integral. So I have to calculate the difference between this point and this point, which is basically 0, because we are integrating from 0 minus to 0 plus, which is a very finite value. If it is a continuous function, the values at 0 minus and 0 plus are same. So basically what we are trying to say is this term is nothing but, say, integral y of t is some y1 of t. So this definite integral is nothing but y1 of 0 plus and y1 of 0 minus. Okay. Now we'll say that a function is continuous at some point k if that function value at k plus epsilon and k minus epsilon are same, then only it is continuous, right? So here that k point is 0. So this function is continuous, its value at 0 plus and 0 minus are same because it's very finite value, just right after 0. So as these values are equal, so this will become 0 because it's a continuous function and its values are same. Now we'll be getting this expression, and they have given boundary condition y of 0 minus is equals to 0. So this value is 0. From this we will get y of 0 plus is equals to 1. So we got y of 0 plus. Now you may ask how this y of 0 plus, what is the use of this? Because anyway we are still not getting y of t. I'll come to this point. So the given equation is dy by dt plus 3y is equals to del t, right? So we have dy by dt plus 3y is equals to del of t. I know that del of t is equals to 0 for t greater than 0. Right. So now I can modify this equation as dy by dt plus 3y is equals to 0 for t greater than 0 condition. And now the boundary condition y of 0 plus, because it is t greater than 0, and y of 0 plus we have got as 1. Now we have transformed or modified the given linear differential equation with impulse input to a differential equation that we have solved few weeks ago or last week and week before that week. So now this is our well-known concept. So we can solve this like a normal differential equation. So it is equals to 0. So it has, what are the solutions? Can anyone tell me what is the solution of this equation y of t? Anyone? It will be a into e to the power minus 3t, right? And I know that y of 0 plus is equals to 1. That implies what is the value of a? Hello. Why no one is talking today? No one is active. I only see two people. Okay. It would be difficult if you don't talk the entire class. Okay, so if we substitute t equals to 0, on the LHS we have 1, on the RHS we have 8 into 1. That means our A is equals to 1. All right. So now my y of t is equals to e to the power minus 3t for t greater than 0. Got it? If I try to draw the graph at t equals to 0, it has the value of 1, and then it will exponentially decrease. So this is how we solve the linear differential equations if the input is the force in input is an impulse. So if the forcing input is impulse, what we know is the integration is 1 from 0 minus to 0 plus. So we integrate it, and then we'll get a relation for y of 0 plus, and then we transform the given linear differential equation for t greater than 0, and then using the concept that we have learned, we'll try to solve it, and then yeah, we'll get this. Okay. Now the first question is, so why this impulse response and or the impulse input, and what is the importance of the impulse response? So one advantage. So let me. So what is the importance of impulse response. So the advantage of the impulse response is now here another topic will also come, which is convolution. Okay. Say we have a system. Some system is there. And say for delta of t, the output is impulse response. So when the impulse to the system gives a response h of t, then h of t is called impulse response. So this is called impulse response because it is the response of the system when the input is impulse. So that's why it is called impulse response. Now for the same system, if the input is x of t, then the output can be written as something called x of t convolution h of t, which means say the output is equals to y of t. Y of t can be written as x of t convolution h of t, where this term is called convolution. Okay, and how is this defined? So x1 convolution x2, or maybe I should use x1 of t because they are time varying function. X1 of t convolution x2 of t is nothing but integral minus infinite to t. So this is defined like this. So this is the definition of convolution. Maybe I'll write convolution. Okay, minus infinite to time period t, x of t or x of tau, x1 of tau, x2 of t minus tau, d tau. This can also be written like minus infinite to time t, x2 of t or x2 of tau, and x1 of t minus tau, d tau. Okay, so this is the definition of convolution. So now my output y of t, if I write it here, I can write my output y of t as integration minus infinite to time t, x of tau, h of t minus tau, dt, or minus infinite to time t, h of tau, x of t minus tau, d tau. Okay. So this means if I know the impulse response of a function and for the same system, if the input is x of t, then I can calculate the y of t directly using this convolution. So let us take an example, series RL circuit. Hello, are you following? Am I audible? Delta of t is also impulse function. Yes, yes. This you should not be confused between, sorry. Okay. You should not be confused between impulse response and impulse function. The response of a system whose input is impulse is called impulse response. So in this scenario, delta of t is the impulse function, and the system is excited with this input. And if the output is h of t, then h of t is called impulse response because the input is impulse and we are checking the response. So that's why it is called impulse response. Now, if I excite the same system with another input x of t, then output y of t can be written as x of t convolution h of t. So this is not star, this is not multiplication, it is called convolution, where h of t is the impulse response. So if I know the impulse response of any system, then I can get the value of y of t using this impulse response as well as x of t. So this is uh, for any linear time invariant system. So again, LTI. This is for any LTI system, linear time invariant. Probably it will be discussed, or probably it has already been discussed in the lectures. linear is one thing and time invariant is another term. So linear time invariant system. So for a given system, say first I calculate the impulse response. Then without solving the system for this excitation, say this system has one differential equation in this format with some input. So instead of solving the differential equation with that particular input, I can use this convolution theorem and get the output. So how is it possible? So let us quickly take one example to understand the same. And if I'm going too fast, you please tell me, because if I go too fast and you do not understand, then there is no point in doing. I'll go slow. So you tell me if I'm going too fast, or if you want me to repeat anything, I'll repeat. Sir, why always LTI? What happens to linear time variant? So uh, all these things. So one. Okay, that's a good point. So what happens to time invariant? So linear time invariant. So when I say linear time invariant, we'll have, say, input is x of t and my output is y of t. Input is x of t minus tau, then my output is y of t minus tau. So for these are called linear time invariant systems. But I mean, if I delay the x of t by some time, then output is also delayed by that time. Now what happens is, if I do not delay this, say this is not valid, which is the case of linear time invariant, then the way this theorem is developed, it will not like meet the requirement that is needed for the derivation of the convolution theorem. So that's why it is not valid for LTI. In the other way, you can, how can you say, okay, let us take one example. Say my impulse response is x of t. Okay. Now I am giving my input x of t. What is my output? My output is y of t is equals to x of t convolution h of t, which is also integral minus infinite to time t x of tau h of t minus tau d tau. Okay. Now if I consider another input 2, which is x1 of t equal to x of t minus t1. Okay. Now for this x1t, my output y1t is equals to x1t convolution ht, which is integral minus infinite to time x1 tau h t minus tau d tau. So x1 tau is integral minus infinite to time t. X1 tau is what? X of tau minus t1 h of t minus tau d tau. Isn't it? Do you agree until this point? I have just replaced using this equation. So x1 of tau is x of tau minus t1. Now what I'll do, I'll consider tau minus t1 to be k. So if tau minus t1 is equals to k, d tau is equal to dk, right? And what will be this equation? Integral, if k is tau minus t1, the lower limit will still be minus infinite and the upper limit will be what? K. What is k limit? If tau is equals to t, what is k? It is t minus t1, right? T minus t1. And yeah, what else? No one is answering. X of t minus is k, right? And h of t minus tau. Tau is what? T1 plus k, right? So h of, hello, hello, are you following? Yes, t plus k. So my tau is T1 plus K. So it will be T minus. Please correct me if I'm making any mistake. Yes, sir. Okay. And dk. Isn't it? Or have I done any mistake? Okay. So just let me check over here. Tau minus T1 is K and H of T minus tau. So T, okay. Now integral, or I'll write it here. So this I'm writing it here. Integral minus infinite T minus T1 x of K H of T minus T1 minus K dk. So T minus T1, you consider it as some variable A. So this you consider it as A. This also you consider it as A. So now integral minus infinite to A x of K H of A minus K dk. This is what? This is what? Can someone say? See, y of t is integral minus infinite to t h of t. Okay, it would be, you will be better able to understand. So y of t is integral minus infinite to time t x of tau h of t minus tau d tau. So now I am replacing tau by k and t by a. So it will be impulse. No, y impulse. So if y of t is in x of tau h of t minus tau d tau, then this value will be equal to y of a, right? Y of a. And a is what? T minus t1. Okay. So I got my output. So for the input x of t minus t1, I got my output y of t minus t1. Understood? So using the convolution theorem, I have first assumed that output is y of t for input x of t. And then I have given input x of t minus t1 and the output I have got is y of t minus t1, because if this is y of t, this will be y of a, right? Y of a is not what? T minus t1. So for x of t minus t1 input, I got y of t minus t1 output, which is what? Linear time invariant. So using this convolution theorem, we can say that for x of t input, y of t is the output, x of t minus t1, y of t minus t1 is the output. So that's why, as this is linear time invariant system, because if this is not linear time invariant, then for x of t minus t1, output is not y of t minus t1, right? So if this is not holding, then the convolution theorem is also not holding, because convolution theorem says that for this input, this is the output, which matches the definition of LTI. And if this is not happening, then that will also not happen. So that's why convolution theorem is only for linear time invariant systems. Did you get it? Okay, fine. Now we'll get back to, we'll see whether if we solve example, then I don't think we'll get time. So yeah, I will quickly take one example, which I was planning to take, which is an RL circuit. R L V of t. Now the differential equation can be obtained as V of t is equals to I of t into R plus L into di of t by dt. Right. Now, if I want to know the impulse response, so here input is what? V of t. Output is what? I of t. Input, I am exciting this system with V of t, and output is I of t. So this is my input. sorry, this is my output and this is my input. So for impulse response, what I need to be doing, I need to be exciting this system with impulse input. So V of t becomes delta of t, and we need to calculate the I of t. That will be my H of t. So we are checking the impulse response. Okay. So my V of t will become delta of t, and the equation will be something like this: di by dt plus R by L, I is equals to 1 by L delta of t. Now, what we'll be doing? We'll be doing the same thing, integrating. And one thing is there, I of t or I of 0 minus is equals to 0. So initially, before giving impulse response, the system was open and it is assumed that the current is 0. So this is the boundary condition. Now I'll integrate it with dt, 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 0 minus to 0 plus, 0 minus to 0 plus, 0 minus to 0 plus. So RHS will become 1. So it will be 1 by L. And I have told that I of t is continuous, right? Or I of t is step. So integration of step is continuous. And continuous for a function, for a continuous function, say f of t, f of 0 plus minus f of 0 minus will be 0. Because it is continuous and the value is same. Now from this we will get I of 0 plus minus I of 0 minus is equals to 1 by L. And I of 0 minus I have assumed to be 0. So I will be getting I of 0 plus is equals to 1 by L. So this is the boundary condition I have obtained for t greater than 0. So until this point, is this clear? There is less than a minute. If this meeting ends, kindly join back so we can continue our discussion. So until this point, is it clear? I have considered one RL circuit and I have planned to find out the impulse response. So what I'm trying to do is I have replaced the input delta of t and then I got this boundary. Now, what I'll be doing, I'll be doing exactly the same thing what I did for the previous problem. What I'll do, I'll rewrite the given differential equation for t greater than 0. So for t greater than 0, my RHS or delta of t is 0, right? So I'll rewrite this equation as di by dt, di by dt plus R by L, I is equals to 0 because delta of t is equals to 0 for t greater than 0. And now my boundary condition is this. This is the boundary condition, right? I of 0 plus is equals to 1 by L. Now it is like a differential equation with no input. And we know the output is I of t is equals to some constant a into e to the power minus RT by L. And I of 0 plus is 1 by L. So using these two at t equals to 0, if we substitute, we'll get the impulse response, which is for a given impulse, the output here in this case current is impulse response I of t is equals to 1 by L e to the power minus RT by L. So this I can also consider as h of t because we are using the same notation, we'll better understand. So for this system, the impulse response is h of t, which is 1 by L into e to the power minus RT by L. Now, what is the advantage of this? The advantage is whatever we have discussed in the convolution theorem, that if I know the impulse response for a given system, then for any input, I can find out the output using convolution theorem instead of solving the differential equation. So for this same problem, if I excite it with a sinusoid or say Vm sine omega t, then my differential equation will be di by dt plus R by L into I is equals to Vm sine omega t. But I need not solve this equation by proceeding with the differential equation because my convolution theorem says if the input is x of t, for a linear time invariant system, then my output y of t is the convolution of x of t with the impulse response h of t. So now I'll consider sinusoidal input for the same function, I mean the same system. And here my input v of t is equals to Vm sine omega t. Now, just to rewrite it properly, my system is RL circuit. Okay. And initially I have excited with the delta of t, V of t, and my output is H of t. Now for the same system, RL, I am exciting it with V of t or Vm sine omega t. Say here, instead of V of t, I would like to call it X of t, so that our notations are uniform and we can easily understand. Okay, so this is my X of t. From the convolution theorem, I know that now this output is X of t convolution H of t. So I check whether if I proceed this way, whether it is giving me the correct answer or not. Because in the earlier week, we have solved the differential equation Vm sine omega t and we got the output for that sine input. Now, instead of solving that, I'll use this convolution theorem, whatever we have studied just now, just to see whether we are getting the same result or not. Okay, so my convolution theorem says my new y of t or my new current for this input is I of t is equals to integral minus infinite to t h of tau x of t minus tau d tau. And h of tau is what? H of tau is this one. So if I replace that, I will get my I of t is equals to integral minus infinite to t h of tau. So this is my h of tau. So this is my h of tau. I have to substitute here. 1 by L e to the power minus r tau by L x of, and what is my x of t? I will also replace x of t. My x of t is my V input. I'll replace that. Okay. So I'll replace that. So x of t minus tau is nothing but Vm sine omega t minus tau d tau. Or in a simplified way, I can also write this as I of t because I know that integral minus infinite to t h of tau x of t minus tau d tau is equal to integral minus infinite to time t x of tau h of t minus tau. Because even if I write this first, write that next, or write that first and write this next, both are same. You can get this from the basic integral. Only you have to consider t minus tau to be some new variable. So if I apply this, I'll get my I of tau is equals to integral minus infinite to tan t Vm sine omega tau 1 by L e to the power minus r t minus tau by L t tau. Okay. I hope you have understood till here, or people who have joined it, I'll tell what we were discussing. So what we were discussing is in the previous a meeting, or because the meeting has ended, we have considered a RL circuit and we have found the impulse response by exciting it with delta of t, and I have found the I of t, which is the output in this system. And this I of t is my H of t, which is the impulse response. Now for any given input x of t, my convolution theorem says that output is x of t convolution H of t, where H of t is the impulse response. So in order to validate that, we have considered a function sine function Vm sine omega t, similar to last week, where we have actually solved the differential equation for this sign. Now, I am substituting this x of t and h of t, and I got this Vm sine omega t 1 by L integral e to the power t minus tau by L d tau. Okay. Now, actually, I can take this small t term out because the integration variable is tau. So I of t, I can write it as 1 by L e to the power minus RT by L into integral minus infinite to time t Vm sin omega tau e to the power minus or plus R tau by L d tau. So this will be the modified expression after bringing the t term outside because the integration variable is tau. Now this has become integration by parts, right? Do you recognize this? Is this integration by parts? Yes or no? So this is my new equation. So is this integration by parts? Yes or no? Anyone? This sine into exponential. Hello. Anyone? Are you following? Okay. Yes, sir. So yeah. Now what happened is this I of t is the output when the input is Vm sin omega t. Yes. So this is my I of t. Now I need to solve this integration by parts to get the I of t. I will not go into the details because we are actually running out of time. So I'll not solve this, but you can solve this during your free time. And if you solve this, I'll write the expression. If you have any doubts, you can ask, or maybe I can solve this later and upload also if you want it that way. So you just tell me in the comments. But I want you to try it first. So if you try this, you will get this I of t. The expression I got, I'm writing here. It will be Vm by square root of R square plus omega square L square because L is there in the this exponential term. We'll get that, and sine omega t minus theta minus Vm by, just have to solve integration by parts, but you give it a try once. If you face any difficulty, you mention in the comment box, then I'll upload the calculation uh, so that you can cross check e to the power minus RT by L. So this is the expression that we will be getting where theta, or where tan theta is equals to uh, how much? Tan theta is omega L by R. Okay. So I'm skipping this part. So trust me that you will get this. So let us, for the time being, assume we have got this solution because I have calculated and cross-checked. Now, what we have done, we have used the convolution theorem to solve this type of problem. And without solving the differential equation with this input, I have used only the convolution theorem. Then I got a definite integral, which needs to be solved by integration by parts. And assume you have done that, you will be ending up with this expression. So now I'll quickly go back to my week 4. So week 4, if I go back quickly, the notes. I just want to show that both will be giving us the same expression. So let me just quickly open the notes. So this is our week 4 notes. So in the week 4, this is the expression that we got. Okay. Or you can also show from here. This is the expression that we got. So let me just copy and paste it here. And then I'll close week 4. Okay. So what if you notice these two, they are just the same here. Sine of minus theta is minus sine theta, minus will become plus, and they are same. So uh, I'll write B because in case someone has missed it, this is taken from week 4 notes. So now if we notice clearly, these two are same. So we have just validated that the convolution theorem is working fine. So what we did is we have considered a RL circuit. We have excited it with the impulse function to find out the impulse response. Then using the impulse response, we have used the convolution theorem for a different input, sinusoidal input, Vm sin omega t. And using the convolution theorem, we have found the output. And this output is exactly the same output which we have obtained in the last week, where we have solved it in a different way. How did we solve? In the previous class, we have considered the differential equation, and then we have used this forced response, natural response approach, and we arrived at the same solution. Instead, we can also use convolution theorem, but there is no such hard rule that you should only use this, you should not use that. Depending upon your ease, you can either use any one of the method, but I just wanted to prove that both will be giving us the same solution. So this completes our first part, the LDE, linear differential equation with the impulse response. Let us quickly solve a few problems. Okay, here we have one problem. Okay, where is this problem? Yesterday I have taken one problem from assignment. Sorry, this is assignment 4. We need assignment 5. So assignment 5, we'll take this problem. We'll quickly do, then we'll dive on to the self and mutual inductance, which is also another critical or very important, I would say. But due to lack of time, I'm going somewhat fast. If you have any queries, you please ask. People who have not joined today, because many people have not joined. I see only 4 members. They can go through later also. But those who are here, you pay attention. If you have any queries, you can ask. So this is say problem 2, because we have already solved problem 2. Again, we have an integral, differential equation. D square y by dt square plus 4y is equals to delta of t, as they have given. The procedure will remain exactly same. First, I'll integrate from 0 minus to 0 plus dt, 0 minus to 0 plus, sorry, dt, and 0 minus to 0 plus dt. Okay, and then now I'll write the equation. So if we have a second order equation, and if x of t is delta t, then d square y by dt square is delta t. So d square y by dt square will have the delta t characteristics, and dy by dt will have the characteristics of u of t, and y will be having the characteristics of, say, r of t. Then integration of y will be continuous. So again, this term will become 0. So I hope you are understanding what I'm trying to say here. Why this term is 0? Because it is a continuous function. So 0 plus and 0 minus value will be same. So it will automatically be 0. and my RHS is equals to 1 because that is what the impulse response, the impulse function is all about. And my LHS can be written as dy by dt 0 plus minus dy by dt 0 minus, isn't it, is equals to 1. Now dy by dt of 0 plus is equals to 1 plus 1, 2. Is this clear until this point? How we are getting? So we are given an equation x of t is equals to delta of t. So we have just followed the way we are doing, integrating from 0 minus to 0 plus, and then using the knowledge that we have gained till now, we got the dy by dt of 0 plus is 2. Is this clear until this point, or if you have any query, you please ask. Hello. I don't know why everyone is calm today and less number of people have joined. Either this I'm going too fast or there could be any reason. So can you solve where integration y dt is not 0? Yes, sir. Which one? No, like, see, the point is to get this dy by dt as well as say in other problems y value at 0 plus, because these values say mainly u of t at t less than 0 and t greater than 0 is different. So they have given the value dy by dt at 0 minus, but we need dy by dt of 0 plus is equals to 2. So in that case, we are considering whatever equation they have given, and as they have given y over here, it is becoming 0. But yes, I'll come to your question. Say instead of y here, if there is dy by dt, I'll get back to your question. But first, let me solve this, then I'll get back to your question. So probably then you'll better understand this. Okay. Okay. So, but for the time being, you just trust me and just try to understand this problem. Then we'll get back to the other problem. Here, d square y by dt square is having the characteristics of delta of t, and dy by dt is having the characteristics of u of t, and y is having the characteristics of r of t, which means y is continuous. So y of 0 plus is equals to y of 0 minus is equals to 2, isn't it? Yes. Then what we'll be doing? We have boundary conditions. So for any such problem, what our primary aim is to get the boundary conditions at t equals to 0 plus, because then we can consider for t greater than 0, this delta of t is 0, because for t greater than 0 it is 0, at t equals to 0 only it is infinite. Then it will be converted into the function that we know, which is d square y by dt square plus 4y is equals to 0 with the initial condition dy by dt of 0 plus is equals to 2 and y of 0 plus is equals to 2 also. Now we know this solution of this, which is y of t is equals to some a1 into e to the power j2t, because the solution are plus or minus 2j, plus a2 into e to the power minus j2t, because this we have learned in previous classes many times, right? So a1 into e to the power j2t plus a2 into e to the power minus j2t. Okay. Now what happens? Now using these two boundary conditions, we need to find a1 and a2. So first I'll do y of 0 plus is equals to a1 plus a2 is equal to 2, and dy by dt of 0 plus, which is a1 into 2j plus a2 into minus 2j is equals to 2. and we'll not get into the details of the calculations. We'll get A1 is 1 minus j by 2, A2 is 1 plus j by 2. Okay. Now, substitute this back in here. Then my y of t is e to the power j2t plus e to the power minus j2t. This is the constant real term. Then if I subtract minus j by 2, then we'll get e to the power j2t minus e to the power minus j2t. Isn't it? Yes. Okay. Now we know that this term is 2 cos 2t and this term is, sorry, this term is 2j sin 2t. Now my y of t will be 2 cos 2t plus sin 2t. Okay, so let us go back and see our answer. So dy by dt of 0 plus we are getting 2, y of 0 plus is 2 and y of t is 2 cos 2t plus sin 2t. Okay, so I'll just recapitulate what we have discussed. The discussion is d square y by dt square plus 4y equal to x of t is a problem with x of t equal to delta of t. Then if we have integrated and then we got dy by dt 0 plus and similarly y of 0 minus is given. From there we got y of 0 plus because y is continuous. Then we have reformed the problem and then we have solved for a1 a2 and then we got this expression. So now as someone must say I have third order equation d cube y by dt cube plus 4 d square y by dt square plus 3 dy by dt plus 2y is equals to delta of t. And say my boundary conditions. So before going into the boundary conditions, I just want to say, so y triple dash, which is this one, y triple dash, y double dash, y dash, and y. So y triple dash is having delta characteristics. So y double dash is integration of that, so it will have u of t characteristics. And then y dash is having r of t characteristics. And y will be having integral of r of t, which is parabolic. If you are taught or just forget about it. Now, what I will do is, I'll integrate it from 0 minus to 0 plus, 0 minus to 0 plus, dt, dt, 0 minus to 0 plus, dt, 0 minus to 0 plus, dt, 0 minus to 0 plus, dt. Now, I'll write step by step. The first term will become d square y by dt square 0 plus minus d square y by dt square 0 minus. That is the first term. And the second term will become plus dy by dt 0 plus minus dy by dt 0 minus. And then the third term will become, say I use a different color. This is y of 0 plus minus y of 0 minus. Then this term will become 0 because I hope you have understood the integration of that is 0 and the RHS is 1. Okay. Is equals to 1 because this is equals to 1. So now how are we saying it is equals to 0 or not? Because we should come from this table, whatever table we have drawn, we should come from there. So y double dash is u of t. So it is discontinuous. So these two are not equal. Okay. And dy by dt is y dash. Y dash is what? Ramp. So these two are equal again. These two, oh, I'm using same notation. So these two are not equal and these two are equal. So this and this will get again cancelled. And y of t is what? Integration of r of t, and that is also continuous. So this one will also be 0. I mean, this will get cancelled and this summation is 0. This will get cancelled and summation is 0. Because dy by dt of 0 plus is equal to dy by dt of 0 minus. Now what I will be getting? I will be getting d2y by dt square of 0 plus is equals to 1 plus d2y by dt square 0 minus. Okay. And so I got one 0 plus condition. Similarly, other 0 plus condition will be, sorry, dy by dt 0 plus is equals to dy by dt 0 minus. This is the other condition. And similarly, y of 0 plus is equals to y of 0 minus. So they will be giving these conditions. They will be giving this, they'll be giving this, they'll be giving this, because 0 minus boundary conditions. So from there we can calculate the 0 plus boundary conditions, and then we can reform the circuit in this format. And the way we have solved here, you can also solve this problem. Only you just have to understand which terms will become 0, which terms will not become 0. And by following the same procedure, you would be able to do that easily. So whoever was asking, I hope now it is clear for you.
I mean,
Yes.
there we are having multiples, right? Coefficients are not equal. Still, we can cancel them.
No, no. I am only cancelling. See, dy by dt 0 plus and dy by dt 0 minus can only be cancelled if dy by dt is continuous. So I will check dy by dt is what? Y dash. Whether y dash is continuous or not. Ramp, r of t, it is continuous. So that's why I'm cancelling. Whereas if you consider this one, d2y by dt square, d2y by dt square at 0 plus 0 minus, which is y double dash. Y double dash is u of t, and it is discontinuous at t equals to 0. So I cannot cancel these two. And similarly, y. Y is what? Integration of r of t, which is again parabolic. It is also continuous. So that's why I'm cancelling it. So you have to be sure which to be cancelled, which not to be cancelled. And that comes from whether the function is continuous or not. So that's why I have written all these terms. So then I will know which term to be cancelled and which term not to be cancelled. So the idea is very simple. For any differential equation, they will be giving the boundary conditions before 0 minus, and I need to find the boundary conditions after 0, which is 0 plus. And if I get all these conditions, then I can consider my RH is equals to 0 for t greater than 0. And with the new boundary conditions, I will solve it in the way that we have solved earlier weeks. So that's what I'm trying to do here. I hope it is clear, but you solve more problems, then you will feel more confident, because if you just listen to these lectures, maybe you'll not be appreciating the concept, but just solve these same questions without looking at my solution. You consider this case and you solve it, or you can consider the problem one, very basic problem which we have considered at the beginning, this problem, and you, sorry, this problem, and you just try to solve it. Then you will understand why we are considering this boundary condition. So because the impulse response delta of t at t equals to 0 is different at t equals to uh, 0 plus is different. And if you consider unit step u of t, it is different at 0 minus and it is different at 0 plus. So the conditions, the boundary conditions at t equals to 0 minus cannot be used for t equals to 0 plus, because there is discontinuity. The value is not same. So in that case, first we need to find the boundary conditions at t equals to 0 plus, which is what we have done here. And then using these new boundary conditions, then we have to solve, because the boundary conditions are different if there is any discontinuous function like u of t or delta of t. So we cannot directly say that the boundary conditions 0 minus and 0 plus are same. For some cases it will be same. So that is coming from whether the continuous is whether the function is continuous or not. If the function is discontinuous, like step function u of t, then you see that 0 plus and 0 minus condition are not same, because of this one that additionally we are getting. It is not same. So this is why we need to proceed in this way, but it will be more clear if you solve few problems. It is not a very difficult topic, but it is somewhat interesting because it is unlike our previous input functions. And if you have any doubts, don't hesitate. Don't think that these 2 hours are the time you have to ask question. If you ask any question in the chat of or the comment section of YouTube video, I'll try to summarize, try to put the solution there. I mean, in the reply also. So don't think that after these 2 hours, if you have any doubts, you cannot ask. And also there is this NPTEL doubts forum where you can post the questions, and the TA, I think Professor Abhishek Chatterjee from IT KGP, he is looking after that. So someone will reply to those questions. So it's not that later you have solved some problems and you are stuck. So you can ask in that forum, because in the forum you can take a picture. It is a mail, so you can take a picture and ask all these things you can do. Whereas in the YouTube comment section, you can ask about the things that I have discussed in this video only. But if you ask, just try to put the timestamps, or say at 37:56 I have this query, so that I'll directly go there and see. So use timestamps and you can ask the doubts there. So it will also help others, whoever is watching that video, they can also see the comments and they can also read it. Yeah. Okay, now we'll go into the second part. So we have 40 minutes left. Yeah, but so self-inductance and mutual inductance. So first we need to identify is how to understand or identify the dots. Okay, so let me just draw one code. Required. Okay, or maybe I should draw a bigger diagram, then it will be better. So here, say the input is there and current I1 is flowing like this. And on the output side, we have say the load is connected in this. Say here the load is connected. Okay, now there is something called dot convention. So this dot convention is very crucial because it gives us the polarity. So for mutual inductance, it will give us the polarity. So the now how to find, say the dot is here for a given winding, whether the dot should be here or whether the dot should be here. So that is the query. So does anyone know how to select this, or any idea?
Mutual inductance might be opposition to the generated EMF.
Yes, yes, you are right. So from Lenz's law, we know that if there is any the polarity of the induced voltage will be in such a way that it will oppose the cause. So the polarity should be in such a way that it should oppose the cause. Now, if I1 is in this direction, so what will be the direction of flux phi, top or bottom? Hello. Say
Flux coming out.
so
Top.
yes, top, right? I hope everyone knows this. Yes, top. So yeah, good. So flux is in this direction. Okay. Now the polarity here is in such a way that it should oppose this flux, right? So here also it should be in this way. So it is opposing, right? So this is opposing. So for this turns ratio, there are two possibilities. One, the current is flowing in this direction. The other, the current is flowing in this direction. So in what way the current is flowing? Say first we assume this direction. If the current is flowing in this direction, how the flux will be there? Top or bottom?
Top.
Top. Okay. And if it is flowing in this direction, how the flux will be there? Bottom, right?
Downside.
Yes, so you are right. So now from the lens law, we know that the polarity should be in such a way that it should oppose. So if this is my current direction, then it is opposing, right? So now this is plus, this is minus because it is supplying to the load. And here if you consider the source also, again less than a minute. So if this meeting can kindly join back. So we have the source here and this is my plus minus. So now this plus minus says that this is my dot here and this is my dot here. So that dot is just for the polarity. So we'll know that which is plus and which is minus, and depending upon the current direction, we'll know which will be the positive terminal and the negative terminal. So as there is less than a minute, I'll just recapitulate what we are saying. Before we go into self and mutual inductance, it is very crucial to understand the dot convention. So using Lenz's law, when AMF is like generated, the induced voltage polarity is in such a way that it will try to oppose the cause, which is the phi generated by I1. So now we know the opposing direction, opposing flux direction. From there we got the current. The polarity is plus on the top and minus here. So from there we got the dot convention. So now how this dot convention helps. So when we take an example, say there are two coils. I'll not be again going into the details of what is leakage inductance, what is all the terminology, because Sir has already gone through, and as we are running out of time, I'll be concentrating more on problem solving, but I'll just give a brief overview of that. So you know that mutual inductance is the voltage induced in the coil 2 because of the current that is flowing in the coil 1, because this flux will be going here, so that will induce the voltage here, right? So because this flux is going here, that will induce the voltage here. So that because that relation between the current and voltage induced is because of the mutual inductance. So here I am considering, so now we have understood the dot convention. Another important aspect is the polarity of the voltages. So we'll be considering two scenarios. So case one, is say we have two coils over here, and this is the dot of these two, and the current is I1T here, and the self-inductance is L1, L2, I2T, and they also have a mutual inductance M2 or M in between. So and the very basic thing is, let us not go into the mutual inductance. First, we'll get L1 di by dt. So if the current is flowing like this, we know the positive signal, positive sign will be here, minus will be here, plus will be here, minus will be here. So the logic is very simple. If the currents are entering dots in both the cases, then the polarity because of the mutual inductance will be same as the self-inductance. I'm repeating, if the currents are entering the dots or leaving the dots in both the cases, in both the coils, then the polarity because of the mutual inductance will be same as because of the self-inductance. So if we draw the polarity, what I mean to say is, So for the coil one, we have one voltage because of the self, one voltage because of the mutual, right? And the current direction are given I1T, I2T, and the dots are given. So first, for any given coil, we need to draw the polarity. So L1 div by dt will have this plus minus, this plus minus. So plus minus, right? And this is L1 di1 by dt, and this is L2 di2 by dt. Now, the mutual inductance will be same polarity if the currents are entering the dots or leaving the dots in both the cases. Both, it should be both. So the same will be getting plus minus, where it is m di2 by dt and m di1 by dt. Are you following? Until this point, is this clear? So the convention is very simple. If the currents are entering the dots or leaving the dots, then the polarity of M or the polarity because of the mutual inductance will be same as this one. I am not saying it will be plus minus. I am saying it is same. So what first you draw L1 di by dt, then use the same polarity sign. If the currents are entering in this way, then it will be minus plus, minus plus, minus plus, minus plus. And both should be having the same condition for this one. Now, for the second scenario, we'll consider one it is entering, the other one it is leaving. So how many cases there will be there? 3 cases. It is entering in both the cases, it is leaving in both the cases, it is entering in one case, it is leaving in the other case. If it is entering or leaving in both the cases, then they will fall under case 1, and only the L and M will be having same polarity depending upon where the current is entering, that side will have plus. So if the current is entering from this side, then this will be plus minus and this will be also plus minus. The polarity will be same. Whereas in this case, if you have any doubts, you please ask, because after this I will be going into problem solving session. And if you have any difficulty understanding this, it will be difficult for you also. So I1T is entering the dot and I2T is leaving the dot. So now what will happen? This is L1, this is L2, and this is M. Okay, so until this point, is this clear to you, everyone? Okay, so the first case is very simple. They'll have the same polarity. The second case is also simple. They'll have the opposite polarity. So first, what is the polarity of this one? Because of the self-inductance, plus minus, plus minus. So now what I'll be doing? First, always I'll redraw the circuit. So it will be easy for me. So first I'll draw two sources. In any problem, you follow this method. So the tendency or the possibility of making mistakes will be reduced. Okay. And now I will draw the current direction. So this is my I1T and this is my I2T. Now what will happen? What will happen? Because this is entering like this will have plus minus, and this is L1 di1 by dt. So first always write the polarity of this one because it is straightforward, and here it is plus minus, and it is also L2 di2 by dt. Now for this case, mutual inductance, it is opposite. Previously it is same, right? Now it is minus plus because it is plus minus. Because it is minus plus, it will be plus minus. So it is exactly the opposite, and it is also very simple. Only you have to understand how to do it. So it is very simple. There are two cases. In the first case, if the currents are entering the dots or leaving the dots, then the polarity of the mutual, because of the mutual inductance, will be same as the self-inductance. Whereas in the other case, when current is entering the dot in one case and leaving the dot in the other case, then the polarity will be just the opposite. So first you always start with the self-inductance, then you draw the opposite polarity for the mutual inductance. I hope this is clear because it is very important, and this is the fundamental thing for our the like rest of the class. Yes, and this is very crucial because if we mess up with one plus minus, if we consider minus plus, then the circuit is wrong and we will not be able to do it also, and we'll end up getting wrong results. So this is very crucial, and that's why the dot convention always, if the circuit is given, then you need to convert this circuit into this circuit. So now we have the polarities, and now we'll know that, oh, okay, so this is the polarity. Now we'll apply KVL, and then we'll simply be getting. So I hope this is clear, and if you have any doubts, you can ask, else we'll go. And another thing, say this has plus minus V1t, and this has plus minus V2t. Now V1t is L1 di1 by dt plus M di2 by dt, and V2t is L2 di2 by dt plus M di1 by dt. Similarly, here if we have plus minus V1t, it is just the basic KVL operation. And if you want to convert into omega, like phasor representation, say if you want to convert this into phasor representation, then replace d by dt by omega t. Omega. Understood? If you replace, sorry, j omega. If you replace d by dt of j omega, then what we'll be getting, say in this scenario, we'll be considering this scenario. If we write the equations in phasor, we'll be getting V1 phasor is equals to j omega L1 I1 phasor minus, this is plus, this is minus, this is plus. Okay. So j omega M I2 phasor. Similarly, we'll get V2 phasor is equal, because d by dt I'm replacing by j omega, I will be I, M will be M. So it will be j omega M minus I1 phasor plus, check my polarity if I'm doing any mistake or not. I think, yeah, for this plus minus, you're not pointing out. I think this will be plus, and this will be minus j omega L2 I2 phasor. So just so we can directly use the phasor representation, and we can solve it easily, which we have started to learn in the last week. So yeah, this we can do. So let me just take one quick example, which will be like helpful to understand the concept better. So now we are in problem 3, self and mutual inductance. So here I have one problem, and the problem is the dot convention is as shown over here, and this is I1t, this is a V of t, and this is shorted, and this is L1, this is L2. They have mutual inductance M. And I to t also they have given, this is I to t. So this will fall under case 1 or case 2.
Same direction.
Yes, case 1. Yes, you are right. So case 1 means it will have the same polarity. And the actual question is find the effective inductance and effective. So what is the inductance that the source will see? So that is the question. But irrespective of the question, first I'll understand which case does it fall under. And as you said, you are right, it falls under case 1. So when it falls under case 1, what I'll do, first I'll draw the polarities, which is very crucial. And if you have pen paper, you can also do, so that you can check whether you have done it in the wrong way or right way. And this is simple. I hope everyone will be able to do. Okay. So the polarity.
I have a question related to this.
Yes.
So
Yes.
if you represent circuits like ways,
Uh-huh.
if inductors are not facing towards each other,
Uh-huh.
mutual inductance might be very less. right?
Yes,
Because
yes. Actually, this is our representation, but it does not mean that they are sitting in that way. They might be
adjacent to
actually
each other.
sharing the same core. You're right. Say some kind of core is there. So inductance one might be like in the inductance is just a wire, right? So one wire might be wound in this way, and the other wire might be wound in this way. So both wire or both the inductance might be sharing the same core, but every time if we draw like this, it would be difficult for us to draw more easily, right? It will not be it will not be easy to draw. So for our ease, we just write as if there are two inductors and they have mutual inductance. This is our representation. It does not mean this inductor is here, this inductor is here. And of course, the mutual inductance will also depend upon the degree of coupling, how coupled they are. So, and the coupling can range from 0 to 1. So depending upon that, it will vary. Yeah, and yes, you are right.
I mean, just want to see that representation. So generally, we'll be having inductors face to face, right? Even in the transformer also, opposite to each other.
Yes,
So in our diagram, we are representing adjacent to each other.
yes,
So
yes.
here the coupling path is only the shorted path. So shorted path will not have much inductance. That's what I mean.
No, 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 no. This
I2 of t is there.
No, this shorting has nothing to do with the mutual inductance. The mutual inductance is between L1 and L2. So this is just the representation. So even if there is a source, that will not, like, this is a representation. So there are two inductors, and the inductor one is excited with voltage, and the inductor two, it is shorted over here, and they have mutual inductance M, and they have this dot convention.
Okay.
And why this representation? Because you can say, then why are you not denoting like transfer function? I mean the transformer. Say we have one circuit like this. Say some circuit is like this. Now these will have say mutual inductance M1, this have M2, and this have M3, and this too has M4. Now it will become very difficult for us to every time draw this in this format, right? It will become very difficult to understand as well as difficult to draw. So we just draw the circuit as it is a normal inductor, and then we'll draw this saying that this has mutual inductance. And now comes the polarity. Depending upon the dot convention, the polarity will vary. So this is just for our ease, but this does not mean that they're sitting quite far. This is only just for our understanding, the denotion that everyone follows. Okay, so now what will be the polarity, plus or minus here?
Plus.
Plus minus. And here also plus minus, because first I will draw L1 di1 by dt and L2 di2 by dt. Now what will be the polarity of M di2 by dt? Is it the same or opposite?
Same.
Same, because it is case one. So yes, you are right. I hope everyone is following. And this has Vt and this is shorted. Now I will apply KVL. So applying KVL will give me two equations. One is V of t is equals to L1 di1 by dt plus M di2 by dt. The other equation is L2 di2 by dt plus M di1 by dt is equals to 0. Now from here I will get di2 by dt is minus M by L2 di1 by dt. Okay. Yeah, someone has mentioned in the chat box it is same. Yeah, you are right. Now I'll substitute this here and write the net equation. Net equation will be V of t is equals to L1 di1 by dt minus M square by L2 di1 by dt. So V of t is equals to L1 minus M square by L2 into di1 by dt. So by V of t supplying I of t will see an effective inductance of L effective equal to L1 minus m square by L2. Passive elements connect to short circuit is 0. Passive elements connect to short circuit is 0. I don't know if you are asking something or you are saying something. I could not follow what you mean by that. So this is my L effective inductance. So L effective is equals to L1 minus m square by L2. So first, for any given such question, first we need to draw this voltage source with polarities. So then we'll understand, okay, this is having plus minus and with these values. So if you want to write in phasor, then this will be j omega I, j omega I2. So we have to replace by j omega. Else, we can just play with the equations to get I1 and I2. So, but the polarity is the main thing, and this is the most important thing also. Okay, now let us solve one problem. As we are having 15 minutes, we will just solve some simple problem. But yeah, any problem will be needing this basic knowledge of dot convention as well as the polarity, everything. So yeah, this is something similar that we have solved. This one will be a bit lengthy. So we can do with this. Yeah, this should be sufficient because the last question is something similar what we have done now. So I don't want to do that again. So we can solve this. So this will be our problem 4. So let me just take a new page. Then it will be easy for you to follow also. So this is my problem. Problem 4. You're able to see the screen, right?
Yes, we can.
Okay. So they are asking I1, I2 and the potential difference between A and B. Okay, it is fine. But first thing is don't look at the circuit and think it is complex. Nothing is complicated. It is just the representation. So this is L1, L2, L3. It has mutual inductance. It has mutual inductance. Yep. So this is problem 4. The everything lies in the polarity. So if you draw the polarity correctly, then it is easy. So let us assume this L1, this L2, this L3. So now we need to check L1, L2 comes under which case, L2, L3 comes under which case. So they have given the current direction. So in L1, current is entering the dot, L2 current is leaving the dot. So it is under which case? Case 1, case 2. One current is entering, one current is leaving the dot.
Case 2.
Case 2, yes. And in the not L2, L3, sorry, it should be L1, L3. Because again, L2, L3 also has some mutual inductance. So L1, L3, L2, L3 also. So L1, L3, current is entering the node. So it is which case? Hello.
L1, L3 or L2, L3?
L1, L3, L1, L3. So this is L1, this is L3.
Both are
Current is
only
entering.
exiting. Oh yeah, okay. One both case 1.
Case 1. And L2, L3?
L2, L3 for one it is exiting, one it is entering.
So
Case
it
2.
is case 2. Okay. So now what I will be doing is say L1, L2, L3 and M, or we can use the values also. First, we need to draw this kind of circuit where we have the polarities. So first, so these two have, so each inductor will have three polarities. Three such voltage sources kind of thing. One is because of the self inductance and the other one is because of two mutual inductance. Okay, so first we need to draw the circuit. Okay, so let me draw this. I think I should draw it a bit bigger. 1, 2, 3. And the input is 100 volt angle 0. And here also 1, 2, 3, and the other 1, 2, 3. It is connected to a load of 40 ohm. Okay. So this is 40 ohm. This is I1 and this is I2. Okay. So first of all, I'll start with this one. So current is entering. So this one will be plus, right? Plus minus. Right? Do you agree?
Yes.
So L1 di1 by dt. Or directly I'll write in the phasor. There will not be any confusion. So it will be j omega into L and they have given the value. So into I. So it will be just J36 into I phasor. So it is J36 into I1. Okay. Now, how about the polarities too? So it is very simple. Those cases which fall under case 1 have same polarity. Those things or those elements which fall under case 2 have opposite polarity. So this and this, whether they have same polarity, 8.4. These two, L1 and L2. Whether it
Yes,
will have the
both are
same
entering.
polarity as this one or it will have opposite polarity. It is case 2,
One
right?
is, yeah, case
So
2.
case
One is
2.
entering, one is exiting.
Yes. So whether it will have the same polarity as this as opposite polarity.
Opposite polarity.
Opposite polarity. You are right. So this is minus, this is plus. Yeah. And for L1 and L3, it is case 1. So it will have the same polarity as this one or opposite polarity.
Same polarity.
Same polarity. So plus minus. Now we have done the polarity. Now we'll come back and we'll write. It is J 8.4 I2. This also J 8.4 I2. So this is so assume this I'm considering L2 and this is for L3. So first I will come with L2. So L2 current is leaving this terminal, is entering this terminal. So first of all, this terminal will be plus, this terminal will be minus, and this one will be L2. So J4 I2, right? Do you agree?
Ah, yeah, right. Plus
Yes.
minus.
Yes. So plus minus. Now L1 L2, then L2 L3. So L1 L2 is having case 2. So whether they'll have the same polarity or the opposite polarity.
Opposite polarity.
Opposite polarity. Minus plus. And L2 L3.
L2, L3, both are entering. So it is same polarity.
No, in L2 it is leaving, in L3 it is entering.
Ah, right. Yeah.
Yeah,
Okay.
so again opposite polarity with respect to this one. So that's why I'm using red color for that one and pink color for the other ones. So both are will be having opposite polarity with respect to the self-inductance because L1, L2 fall under case 2, L2, L3 also fall under case 2. So now this will be J 8.4 I1 and this one J 11.2 I2, right? Because one is with respect to I1, the other one is with respect to I2 only because the L3 is also carrying I2. So you should be very careful with this. Okay. Did you understand this one? One is with respect to L1. So current is I1 and the mutual inductance is J8.4. The other one is with respect to L3. The mutual inductance is 11.2. Current is I2 because I2 is only flowing here. Is that clear?
Yes.
Yes. So now for L3, current is coming from bottom. So this will be plus and this will be minus, and the self-inductance is 49. So J49 I2. Now L1 and L3 is case 1. So whether they will have the same polarity or the opposite polarity.
Same polarity.
Same polarity. So this is plus, this is minus. And L2, L3?
L2 is leaving, L3 is yeah, L2 is leaving, L3 is incoming, opposite. Case
Opposite
2.
polarity, right? Minus plus. Fine. Is this clear? Hello.
So self-inductance is opposite, right? For this.
So this is the self-inductance, and this is L1, L3. So L1, L3 is case 1. So they are having the same polarity. So this is
As a self.
J8.4 I1. Because this is with the L1 and this is L2, L3. They are having case 2. So it is having the opposite polarity. So this is J11.2 I2. Right? Got it? The polarities, everything? Everyone. Okay. Someone has answered. Sorry, I was not checking. If your answer is matching, because I do not know for which you have answered what. I'll just repeat again. For any given problem, just don't write any equation before drawing this diagram. So first you need to understand how many sources will come. So how many sources will come? One source is for self-inductance, the other sources are for mutual inductance. So each inductor is having two mutual inductance and one self-inductance. So each inductance will have three sources. First, you identify the mutual inductance, whether they are falling case 2, case 1. We have identified. Then coming to L1, as current is entering here, that terminal will be plus minus. So now when you come to L1, L2, the case is 2. So it will have a opposite polarity. So if this is plus minus, this is minus plus. And L1, L3 will have case 1. So if it is plus minus, this is plus minus. Similarly, L2, current is entering in this polarity at this point, right? So this terminal will be plus, the other terminal will be minus. Now, L1 and L2 will have case 2. So this has opposite polarity. L2 and L3 is also case 2. So that also has opposite polarity. And I have written the voltage expressions, which is the impedance into current. Now coming to L3, as it is entering from the bottom terminal is plus and minus. With respect to L1, it is having case 1. So the same polarity. With respect to L2, it is having case 2. So it is the opposite polarity. Now I have drawn all the polarities, everything. So now if I have to make any mistake, I had to do while making polarities, but I had made sure that I have not made any mistake. Okay. I hope you have understood until this point. Now this is 100 volt angle 0, right? So now I'll apply KVL in this left side as well as KVL in the right side. So let me just zoom out somewhat a little bit. So now you can see the full screen. So here we'll write one equation. Here we will write the other equation. So equation 1, can someone tell me what it will be? Say this is plus minus. It will be 100 angle 0 minus J36 I1 plus J8.4 I2 minus J8.4 I2. Isn't it? Is this correct? I have started from this point and I have circulated in the loop. So from here to here, it is increment in the potential, decrement in the potential, increment in the potential, decrement in the potential. So this is one. You understood, right? Hello. How we got KVL in the left loop?
Yeah.
Yes. So this and this will get cancelled. And what is I1? I1 is nothing but 100 angle 0 by J36. Can someone calculate and tell me what is the value of I1? Hundred by 36 is the magnitude and minus 90 degrees.
2.77.
Yes, 2.77
minus 90 degrees.
minus 90 degrees ampere. So my I1 RMS is 2.77. Now I'll apply KVL in the second equation. So I'll again start at this point and then I'll circulate. So first I'll have decrement in the source potential. So minus J49 I2 no, it is not ready. Sorry. Minus J49 I2 and then I'll get again minus J 8.4 I1 then plus J 11.2 I2 then minus J4 I2 then plus J 8.4 I1 and then we'll have plus J 11.2 I2 and then the resistor is decrement, so minus 40I is I2 is equals to 0. So now if you can see I1 terms are getting cancelled. So there is only I2 term on the LHS side and 0 on the RHS side. So what will be the value of I2? 0 amperes. So there is no current flowing in the second side, I2. Is this clear? We'll just quickly check whether it is the case or not. So I1 value we are getting 2.77, it is falling. I2 value is 0, so it is matching 0. Now they are asking what is the RMS value of the potential difference between A and B. So this point is A and this point is B. So AB is nothing but the potential difference across this
L2.
inductor.
L2.
Hello, someone is saying something?
L2, across L2.
Yes, yes. So using a different color, say this is my A. So this is my B. So if I write I2 is 0, right? Simply I2 is 0. So I will only consider I1 terms. So now I'll be getting, yes, someone has mentioned 0. You are right, Amit. So now VA minus or plus J 8.4 I1 is equals to VB. Do you agree? Because I2 is 0, I will neglect this to be 0, this to be 0. Only I1 term will be there. So VA plus J 8.4 I1 is equal to VB, right? From here to here, there is increment. VB is at a higher potential. Hello. Because I2 is 0, I will just remove these two and VB is just VA plus J 8.4 I1. Do you agree? Just small KVL. Okay. So VAB is minus J 8.4 I1. So now VAB is minus J 8.4 I1. So substitute this I1 here and tell me, can you tell me the value of VAB? RMS and angle. I want R angle theta form.
23.26 is the magnitude.
23.286. Okay.
268 magnitude, and angle is
268 or 286?
268.
Okay, 268.
Angle is minus 90 plus 90. Oh, minus 90, minus 180 degrees, right?
So minus 180 or plus 180. Okay, whatever. I hope everyone is getting this because this calculation I have not done. So if there is any mistake, kindly check. So the RMS value is 23.286. So 23.2. So it is falling in the region. So we are getting the same answer as whatever they have mentioned. So yeah, this part is very crucial as well as very interesting, and the possibility of making mistakes is very high. So you have to be very careful. I'll quickly summarize. In the beginning, we have discussed the impulse function and the area of impulse function, followed by a quick problem where we'll integrate from 0 to 0 minus to 0 plus. And the main aim is to find the boundary condition for 0 plus. Then we'll convert this into a zero input solution and sorry, zero input condition. Then we'll solve for the natural solution, and then using the newly obtained condition, again there is less than a minute, so if this ends, kindly join back. So using the new boundary condition, we'll solve. Then the importance of the impulse response is we can apply convolution theorem. We have discussed convolution theorem. Then using one example as series RL circuit, first we found the impulse response. Then for sine input, we found using convolution theorem what is the output, which is exactly matching with the one we obtained in the last week. Then for problem 2, we have considered second order system. We have exactly followed the same way. We just want to find the boundary conditions on the 0 plus side, and we got it. And now using that, we have solved this equation, and we have considered a third order equation. And similarly, we just have to find the 0 plus condition. Using this condition, we have to reframe it and then solve it further. So until this point, if you have any question, you please let me know. I think this meeting will end. After that, I'll summarize what we have learned in self-mutual inductance. And if you have any questions,
Still not coming. Oh yeah, now I can see.
okay. So in the second part, we have discussed self and mutual inductance, where in the first earlier discussion, we have discussed how to identify the dots using Lenz law, and we have understood the dot convention. Then using that, we have understood the polarity. There are two cases. In the case one, they'll have same polarity if the currents are either entering or leaving the dots. In the case two, if one is entering, the other one is leaving, they'll have the opposite polarity. And using one quick example, we have understood the polarity. Then we have solved one previous year problem. First, for any question, first you identify whether they fall under case 1 or case 2. Then after understanding that, you draw the voltage sources with proper polarities. Now, after doing this only, you start writing the equation, else you will end up making mistakes. So just follow the exact procedure. So then the probability of making mistakes will reduce. Then we have applied KVL, KCL, and then we got I1 and I2. Yes, with this, we can conclude. If you have any questions, you may ask.
Just one question,
Yes.
right? In the dot convention,
Yes.
they are giving the dot as well as the current direction also, right?
Yes, in our questions, yes.
Yeah, in one of the questions, right?
Yes.
So there, I just want to understand that why are we doing same convention means plus opposite conventions. So just want to understand that. Can we go to one of the problems
This problem.
where we have, some assignment kind of problem that we have seen, right?
Yes, this problem.
Yeah, here. So in this, right, J36 side, on the L1 side, it is coming
Yes.
inside, right,
Yes.
towards
Yes.
the dot.
Yes.
And whereas the L2 side, it is leaving, right?
Yes.
Current is leaving.
Yes.
But what this dot significance? I mean, so it is supposed to be like current direction, right?
Yeah, no,
Dot
dot is not current direction. See, here, like the dot, like talks about, how these are bound and how the flux is, like deciding the polarity. Say if no current is flowing in this I2, say
Okay.
current is only flowing in this I1. So flux is this, and flux will pass in this side, right, from top to down.
Yes.
Then how the polarity is coming over here? So instead of doing that, first the polarity or the dot convention is defined, and now we went using that dot convention. Say if these two dots have something like this, and if the current is entering the dots, then how the mutual inductance polarity is dependent. So it's like, say current I1 is flowing in L1 and I2 has no current, but because of the mutual inductance, there will be induced voltage here. So how that is coming? So that is this is all about.
Oh, you mean maybe I can apply that right hand thumb rule so that
Yes,
I will
yes,
come to the
yes, yes, yes,
right hand thumb rule and lines law both.
yes, yes, yeah. Right hand thumb rule and lens law. Yeah, you are right.
Okay, okay.
Yeah.
So in the same problem, can we scroll down that? Last question only, just want to
Mhm.
understand. So here in this case,
Yes,
J36, through that it is flux towards the L2 side. I mean current is going flowing down, so
yes,
flux is towards the L6 and the reverse direction,
yes,
and I2 is going up, so it is I mean flux is in both the cases opposite in nature, right?
yes.
One is going up and another one is coming down.
No, again, one more thing. Yeah, like one more thing. I will not ask you to correlate with this. Here, the flux direction depends upon the winding, right? If whether it is clockwise wound or anti-clockwise wound.
Okay,
Okay, because here it is wound in anti-clockwise, and here it is wound in clockwise. So if it is the other way, then the flux direction will change. So you cannot correlate this example with this diagram because we do not know the winding direction. So instead of knowing the winding direction, if we know the dot itself, then we'll get the polarity using this cases that we have discussed. So in any of these problems, they will not say how the wire is wound, whether it is wound in clockwise direction or anti-clockwise direction, even though you can get from the dot convention, if this is in this direction, this should be in this direction. But without going into further into that wire wounding, we'll say that if the current is entering the dot, then because of the mutual inductance, the polarity will be positive or negative. So they have denoted a dot convention that is followed universally so that there will be no confusion, and this is much easier because every time say I have given this example, now every time you have to see, okay, the flux is going top to down, how that will reduce. So this will be complicated, and every time we cannot draw this kind of circuit, because if there is L3, then again you have to draw the winding and see the flux direction. So in order to avoid all these things, they have come up with this dot convention, which is much easier, and they have uh, using this thing, they have come up with these two cases, how the polarity will be.
okay.
So that has been
They
done
have
before,
simplified.
and
Okay.
these are the result of that thing.
Hmm. Okay, they have simplified it. Anyway, they have
Yes,
considered the
yes,
direction of the
yes,
current. Okay.
yes.
Hmm.
But I would ask
Okay,
you
just like
to take one example, give dot convention, and from the flux, you can check whether this is coming or not. That you can do. But yeah, that from
I
there
mean,
you will
the
understand.
flux, the dot is saying that flux is coming towards or outwards. How can know that based on the dot
Say,
convention?
So
It is
let us consider this example. So here, if the wire wounding, how it is wound, if it is given, then we can get the dot, because from the Lenz law, the voltage polarity should be in a way that it should be opposing, right? So
yes,
we
right.
have considered I1 in this direction, so the flux will be uh, from bottom to top. So if this flux is in this way, then the polarity here should be in such a way that it should oppose. Say there is load, and if this is plus
Hmm.
minus, current will be flowing in this direction. So if the current is flowing
Oh,
in
I am
this
understanding.
direction, then the flux will be like
Okay,
this.
okay.
So from there,
Hmm.
we got the dot convention.
Okay. So opposition. So
Yes,
where opposition
yes,
is coming.
yes,
Okay.
yes,
Mhm.
yes. So if they
So
give
it is saying
the how the wire is
Hmm.
wound, then you can get the dot convention. And once the dot convention is given, it is up to your choice. But usually this is much better because here there is no phi business, whether it is going top to bottom, bottom to top. It is very simple. If it is entering same polarity, if it is different, then it is opposite polarity. But you can still
Okay.
get this from here also, which you can try later as your homework.
Okay, but here also they are not talking about anything related to self. Only the dot convention is between mutual only, right? They are
Yes,
not
yes,
talking about
yes,
self.
yes, yes, yes. Self does not
Okay,
have any dot convention because self is very
that's
simple. If
hmm.
the current is entering with the at terminal 1, it will be positive. If the current is entering at terminal 2, that will be positive. Whereas in the case of mutual inductance, it depends upon how the current is entering here and current is entering there also. So that's why, because of the dot convention. Yes.
Okay. Thank you. I
Yes.
think I took so much time. Thank you.
Yes, but I completely or fully suggest you to draw or solve some problems. So then you will better understand the dot convention. And also, if you want, you can see for a given example, you assume dot convention and see if the current is entering in both the cases and leaving in both the cases, how the polarity is changing, and then you can correlate with case 1 and case 2. But that you can do, but don't confuse yourself. Yeah.
Okay, yeah.
Okay.
I understand. Anyway, I got the point actually. So
Yes.
even the current directions are different. Let us say
Yes.
one is entering, one is going, one is entering, and one is exiting.
Mhm.
At that time, your flux is going to be opposite in nature,
Yes.
but the opposition from the second side will be aligned with the first one. So it will
Yes.
be like added up.
Yes.
Okay.
Yes, that direction you need to check how. So for like you can consider this example and you can try. I1 is also entering,
Mm.
I2 is also entering the dot. Then see here the flux is going from bottom to top. If this is entering, then it is going from top to bottom. So both the fluxes will get added up. So in that way you can
Mm.
do. Yeah, that will actually be a very good practice. It will help you understand the concept better. Yeah, but
Right? Because sometimes we are directly
yes,
blindly
yes,
we are
yes.
following the.
I completely agree that you need to do this exercise. So then, even if you forget this, you can get the concept from this, which is actually,
Yes,
yeah,
yes.
you're right. You should not blindly.
Maybe 15 seconds, 30 seconds it will take
Yes,
to
yes,
recall
yes,
that concept. That's
yes,
all.
yes,
Okay.
yes.
Thank you. Thank you
Yeah,
very
yeah.
much.
Thank you. All the best for your assignment. See you in the next week. Good night.
Thank you. Good
Uh,
night. Bye bye.